everybody. I'm very happy to be here, and it seems that the microphone is still not working. I give it another try. I'm very patient. Now I hear we are coming up, and that's great. So thank you very much for being here, for your interest in this session. It's session 03.3. It's on on-site inspections, inspection techniques. My name is Gregor Malich. I had the pleasure of working with the OSI division for many years on the development of these techniques, together with my colleague, or former colleague, Alet Rollins, next to me. And we will be convening this session, which will feature 4 talks. We have a special arrangement for this session. We have 2 talks before the coffee break and another 2 talks then right thereafter at the same place. Now, on-site inspection techniques are probably one of the core areas of work for the CTBTO since the beginning. They are listed in the treaty, paragraph 69, part 2 of the protocol, and a constant element in the development of these techniques has been that knowledge has been gained and technology has advanced at the same time. So in order to ensure that the OSI capabilities are as strong as possible, but in line with the treaty provisions, the organization certainly has to look into what capabilities exist, and this is a forum for discussing new ideas, and I look very much forward to hearing the first talk from Yuri Bergman. May I ask you to take the floor? And his talk will be on a method for estimating the tripartite array Back-Azimuth error caused by the far-field approximation. Thank you very much, and Yuri, it's yours.
Yeah. My name is Yuri Bregman. Work together with Yochai Ben-Horin. We are from Israel National Data Center. First, here is the outlet of my presentation. First, I will speak a bit about the motivation. Then I will make some theoretical formulas and estimation of plane wave error after the case study, and at the end I will give some summary. So the tripartite microarray became a major tool for the passive seismic phase of the on-site inspection. During this phase, up to 50 microarrays are deployed in the inspection area with distances about 5 kilometers, and the goal of this deployment is to detect and localize events with magnitude up to -2. That means that many events would be detected only for one single array. And the main advantage of using a microarray is possibility to estimate Back-Azimuth. But because of the short distances, the plane wave approximation is broken, and the Back-Azimuth actually will be biased. So our goal is to estimate this bias and to correct the Back-Azimuth estimation. So this consideration is not theoretical one. For example, during the integrated field exercise in 2014 in Jordan, one of the events was very close to the array, and this where plane wave approximation is broken. So, to our opinion, this should be taken into the consideration. So here is a Back-Azimuth formula under the far-field assumption, which depends on array coordinates and arrival time differences. We define the Back-Azimuth plane wave error as a difference between the true Back-Azimuth and Back-Azimuth computed under the far-field assumption. And our goal is to estimate this error and correct the Back-Azimuth, of course. We developed a formula using actually simple math, which this error can be computed. Analyzing this formula, it depends, of course, of the epicenter distance, but it is independent of wavefront apparent velocity. And also, this formula is invariable under similarity transform applied to the array, reference point, and the epicenter. We make some theoretical computations for simple configuration for isoscale triangles with different vertex angle. Of course, it depends on it. And it's possible to estimate the maximal plane wave error. As you can see here, when the minimum error is when the triangle is irregular. Up to now, it was only theoretical considerations, but we also show some case study showing that actually this is important to take into account. We use some unknown event near the Mount-Meron seismic array. To remind you, the IMS seismic array is collocated also with infrasound array IMA. Using seismic stations of the array, using grid search, we localized this event and use the tripartite array including 3 infrasound stations, AMI 1, 2, and 3. There is some error on the slide, where the distance between reference point was about 1.5 kilometers. First, we computed the theoretical Back-Azimuth, and theoretical plane wave error, which actually is not so small, 13.8 degrees. Now, using the acoustic waveforms, actually using arrival times, we estimated the plane wave error using our formula, and actually the estimated plane wave error is 13 point. That means that we actually can reduce the plane wave error using our formula. Summary. We have analyzed the plane wave errors, that means errors caused by far-field assumption. New computational formula for Back-Azimuth plane wave error were developed. Back-Azimuth error are a result of system geometry depending only on epicenter position, station location, and reference point location. Case study demonstrates that the errors are not theoretical issues only, but can be significant in real measurements. We strongly recommend to take the errors into account for array aim to measure low magnitude events during the passive seismic phase at the on-site inspection. For the details, please see our paper in Seismological Research Letter. Thank you very much for your attention.
Yeah, thank you very much, Yuri. I open the floor for questions. So maybe to just break the ice, question to Yuri. Now, you know the inspection team will have a size of maximum 40 inspectors in the field. They have limited resources. So how to assess in field conditions when the error needs to be taken into account? Is there some of a procedural guidance that you would recommend?
First of all, I think that the inspector should consider this error. And I think that the formula is not so complicated. Actually, they can compute it. Maybe if maybe it should be added to the software. Yeah, that they have some formula built in. Yeah.
And that would be happening in real time then during the deployment.
What?
That would happen in real time during the deployment.
Yeah, the formula is very simple. Yeah, but of course, under the pressure, it's a problem. But maybe if it should be considered to put it some button in the software.
Okay, thank you. Can we just get a microphone for Yochai?
I think that adding a thought on that it's that you can assess after you're installing the system, you can assess well what is the distance where the far field approximation is breaking down. And then you can decide where you really need to include this in the analysis or not. And you can say, okay, if this is an event of 200 meters, 400 meters, near the array, I probably need to look on that. But if it's 3 kilometers from the array, I can use the regular formula. And it can give you, and the importance that, especially if we want to pin out and to say it happened here, and it's very close to the array, we might miss the point. So it doesn't need to be included in real time. It can be included in advance to assess the performance of the array that we are installing.
Okay, thank you very much. Any other question to Joey? Yes?
Thank you for the insightful presentation. Do you consider the number of events?
Excuse me?
What the number of events?
More events.
Events considered in the course of your study. The number of events recorded in each station. Were they considered or put into consideration?
You are speaking about our case study?
Yes, please.
Actually, there was other events. We also, in the paper, there are some different configuration. We used also different configuration. Just if you are interested, just look in the paper. Yeah, there's some another configuration and another computation. And actually, it's possible. The data is open. You can take it and to check.
Thank you. I think we have time for one more question, if there's any. Well, then, thank you, jury. And I may ask the next speaker, Brian Milbrath from PNNL. And he will be talking about a comparison of portioning samples under the Comprehensive Nuclear Test Ban Treaty Organization, the Organization for the Prohibition of Chemical Weapons, and the International Atomic Energy Agency, sort of focusing on a different inspection technique compared to the first talk. Thank you, and the floor is yours.
Thank you. So this will be the least technical talk I've ever given as a scientist, so my apologies for that. But history and policy can be interesting too. So I've been involved with CTBT for a long time. My two co-authors, Jonathan Foreman was an inspector in the OPCW for many years, and Stefan Voigt, who's retired from PNNL, used to run one of the IAEA labs in Cybersdorf. Next, please, or I can do it, can I? Okay, so in the treaty, it says that the inspected state parties shall have the right to retain portions of all samples collected when these samples are analyzed and may take duplicate samples. And OSI manual sessions in Working Group B have struggled with this section for a long time and how to reach a common understanding of what it means. There's a couple problematic areas in this part of the treaty. In particular, what does get a portion when analyzed mean? Does that mean after it was analyzed? Can that be before it was analyzed? Taken literally, does that mean during its analysis? If it can be done before analysis, could it be significantly before analysis, like right when it's taken in the field, perhaps? And also, what is the role of duplicate samples versus these portioned samples? So, like the CTBT, the CWC involves inspections and taking samples. And the CWC was negotiated and drafted just a few years prior to CTBT, involving many of the same diplomats. And CTBT's language on sampling appears to be inspired by CWC's. So reading from CWC, it says the inspected state party has the right to retain portions of all samples taken or take duplicate samples and be present when samples are analyzed on site. So if I show those two phrases right on top of each other, you can see that the CTBT is similar but a little bit different from the CWC language, and there's two key differences. Maybe the minor one being that CWC uses the word or between portions and duplicates, whereas CTBT uses and then the larger difference being where the clause when samples analyzed is located in the text. So in CWC, it's referring to being present during the analysis, and in CTBT it talks about taking the portions when analyzed. And so John Walker of the UK Foreign Affairs Office would always quip that perhaps a quick bad transcription from CWC to CTBT has led to a big headache for Working Group B on this issue. And so I was inspired with John Walker's retirement a year or so ago to look into this a bit more on how the CWC, or the OPCW, which is the agency that implements the CWC, does sampling, and why not do IAEA at the same time? So the OPCW has three types of inspections. Routine inspections related to things like old chemical weapons facilities, challenge inspections called on a short notice by one state party due to concern in regards to another, and investigations of alleged use. The latter two are a lot like what we have in CTBT, OSI. There's a requesting state party, an executive council vote, you get to a limited inspection area, and so forth. Neither of those have ever been requested. That may be a surprise to you because we've heard about OPCW inspections in Syria. Those were called something else, some new mechanisms. I'm glossing over stuff. If you're an OPCW expert, I apologize, but it's a 12-minute talk. Some of the new mechanisms were used in Syria. So this is an example of how splitting is done by the OPCW during routine inspections. And I find it interesting when you look at the documents from the OPCW, they actually use the word splitting, where we colloquially always say splitting, but we know that the treaty says portioning in CTBT. But for example, they have a process to take material on site, solid aqueous or material extracted from wipes where they're pouring a solvent through a wipe and then splitting the solvent. Splitting them into 8 portions. I pulled this out of an internal document. 2 are for on-site analysis by the inspection team. 1 is chosen by the ISP for retention. They can request joint custody, and the remaining 4 or 5 are for off-site analysis if it occurs. They even have a nice little holder there for their 8 samples. Just a couple notes about OPCW. Chemical degradation is a big problem for them, so they don't worry so much about reproducibility of analysis that maybe we do. Routine industrial inspections rarely involve analysis, and if they are done, they're always done on site. The non-routine inspections that have happened in Syria have resulted in samples that were brought back to the OPCW, but they weren't really split on site. And duplicate samples were sometimes taken by the ISP in Syria. Now in the IAEA, they have on-site inspections too under their comprehensive safeguards agreements. They have ad hoc inspections to verify a state's report or any changes. They have routine inspections at nuclear facilities and other locations with nuclear materials. And they have special inspections that if they have some information from the state or routine inspection that weren't adequately addressed in the others. And safeguard measurements involve bulk nuclear material samples to verify the correctness of a state's declaration, and environmental samples, which was a bit more relevant to OSI, to verify the completeness of a state's declaration. The bulk material samples involve a single sample packaged by the state for the IAEA. Any portioning, it just goes to Cybersdorf. It's interesting when you talk with IAEA people and you talk about portioning, they immediately think of what they're doing in Cybersdorf, where they ship it off to multiple labs, but that's post them getting it from the ISP. Environmental sampling done by the IAEA at a facility involves swipes 90% of the time, plus occasional other matrices. Now, a typical swipe sampling kit with IAEA is 6 swipes, our standard, I should say. At least 4 of those the inspector has to bring back to the IAEA. He or she may leave 1 with the facility operator. The IAEA does not split swipes. They have found it adequate to just take the same swipe at the same multiple swipes at the same location or adjacent locations, and then just hand the swipe off to the facility operator. They don't really do joint custody per se, but they sometimes do leave samples under seal while they try to get a shipping arrangement worked out. And both the OPCW and IAEA, when I would ask people about what do you do about the duplicate samples, and in those organizations they feel, well, an ISP can take whatever duplicate samples they want, nobody questions that, but there's not this idea that they have some sort of status that some have wondered about. So what can we learn from these other treaties about sampling? Well, I think a few things to note. One is that portioning for the ISP in other treaties is always done at or soon after collection, and is never done around the time, during or after IT analysis. It's always done in regards to when the sampling occurs. We have had technical arguments in Working Group B about why that's a good approach. The IAE accomplishes portioning just by taking multiple similar samples, while the OPCW does perform some actual splitting in their case. So maybe both approaches are valid. And the ability of the ISP to take duplicate samples is a given, is understood, but those samples don't necessarily have some sort of status within the verification regime. And the other treaties have established practices already in existence on how to, something that we can look forward to in the future, on how to keep portions under joint custody or seal in the ISP. And with that, I look forward to your questions. Thank you.
Thank you, Brian. I open the floor for questions. Franz.
Thank you, Brian. I noticed one difference also in the text between the OPCW sampling and analysis and the CTBTO, and that is the CWC performs sampling and analysis to confirm a negative, to confirm the absence of scheduled chemicals or chemicals that are prohibited under treaty. And the CTBTO performs sampling and analysis to perform a positive confirmation of the presence of relevant radionuclides. And I wonder if that simple difference in text may help you in your deliberations during Working Group B to hammer this thing out.
Well, that's an interesting observation. I hadn't thought of that. I don't know that it solves the problem, though. And, I mean, in both cases, the reason that an ISP wants a sample is that it would like to, putting words in the ISP's mouth, it would like to either perhaps learn what the inspection team is learning, or it may be wishing to refute something that the inspection team claims based on its sample. So in either, whether you're proving an absence or a presence, I think that works the same in either way. You're still going to use those. It may be a little harder in OPCW when you're trying to, so we're only looking for a few things in CTBT. In OPCW, you could be looking for a lot more things, and to show the absence of all the various chemical weapons could be a bit more of a challenge. But thank you.
Thank you, Brian. Are there more questions? Okay, Gustavo, yes.
Yeah, thank you, Brian, for your presentation. I wonder whether you analyze also the type of analysis that the sample undergo after the sampling and after the splitting of the samples. In CWC and IAEA regime, you have two types of analysis. One are destructive and non-destructive analysis. So I wonder whether you analyze or you give a thought on what they are going to do with the samples.
Well, again, I was more focused on the actual portioning and what the organizations and the states felt about the samples than the particulars. I'm certainly aware that the IAEA does both destructive and non-destructive. But again, if you want to give the ISP's sample status, you need to have a process that's reproducible. And the IAEA, by doing destructive analysis, that's not going to be, you're not going to revisit that sample. So what the IAE does to enforce reproducibility upon itself, basically, is they split the sample before they do the destructive analysis. So there's always this question about, it's addressing, the reason they do splitting in those two organizations is so that they can have two independent labs verify something, which we don't currently do in OSI. We just talk about one lab. The lab could remeasure the sample if needed, probably would if it was the key piece of evidence, but it's not destructive analysis. And then again, if you do destructive analysis, even if the ISP has their own sample, if it doesn't have any status about refuting the argument of IAEA's sample, you don't need to worry about that too much.
Okay, thank you again, and there's one more question from Peter.
Yeah, maybe one more aspect of the portioning is the issue of homogeneity of the samples. Did you elaborate on that in your analysis? So a difference particularly between the OPCW and OSI for CTBTO?
So certainly when we were in Working Group B talking about technical reasons about when to split the sample, we worried a lot about homogeneity. And when we were talking about these things in Working Group B, that's part of the argument for doing it early in the sampling process. I did not look at it purposefully for the other organizations. I was charmed, though I will say, by the OPCW documentation I saw about how you take a pile of dirt and you slice it into 4 piles, and you take these 2 piles and you put them with these other 2 piles, and then you take your spatula. The words mixing bowl and spatula are in the OPCW documents. And then you take your new piles and you split them this way and that way and mix them. So certainly the other organizations have cute ways to homogenize their samples, and we should also in OSI, but I did not, again, to me that was secondary to just the status of the portions and how to, when in the process to do the portioning. Thanks.
Okay, thank you, Brian. I think the time is up for the first part of our session this afternoon. So we'll go now for a coffee break, and we'll hopefully meet again at 4 o'clock to continue with our second part. So thank you, and see you soon.
Good afternoon, ladies and gentlemen, again. If you could take your seats, please. We'll be starting the second part of session 3.3 now. So welcome back to session 3.3 on on-site inspections. And this is a very diverse session. We've already heard about passive seismic monitoring and environmental sampling. In the second part of the session, we have a presentation on a topic close to my heart involving multispectral imaging. And finally, we'll be concluding with a presentation on unmanned aerial vehicles. So first of all, I'd like to invite Brendan Crawford onto the podium to talk about explosion anomaly detection from thermal infrared photogrammetry. Brendan, you have the floor. Thank you.
Hello. Excellent. My name is Brandon Crawford. I'm from Los Alamos National Lab, United States of America. And I'm going to talk today about explosion anomaly detection from thermal infrared photogrammetry. I'm here representing our team from LANL, who works on UAS, especially in this world. I'm excited to talk to y'all. So I'm going to start with a brief outline of today's talk. I'm going to talk about our team, what we do, and how we accomplish it. Give a brief background on photogrammetry in general. And then we'll talk a little bit about what thermal imagery is, what it's used for in our case, discuss a specific study we were able to be a part of, talk about the methods, how we were able to process the data and get to our results. And finally, we'll close some thoughts about ML and AI methods within the ArcGIS Pro platform, which could also be used in other systems, and wrap up some conclusions and thoughts about this work going forward. So first things first, our team at Los Alamos seeks to develop and employ tools that can work towards automating relevant signature detection and discrimination in complex natural environments as well as within engineered environments such as test beds. We try to drive towards real-time signature detection. And importantly, we develop, refine, and test these tools in operational environments. One such tool that our team has found a lot of success with is structure from motion, SFM, photogrammetry. This is a technique wherein multiple photo pictures are taken of a location, typically in traditional RGB imagery, and individual pixels from each of those photos is located in each of these sequential photos, and the location of that point in space and also the location of that camera relative to those points in space is identified. From this, you're able to do two things: create a decent and high resolution accuracy 3D model of a surface, as well as be able to create large-scale orthoimagery where all these photos are stacked together of a large site and tie those two together. Some of our previous work within this team has really pushed the boundaries on the resolution and accuracy of surface change following some subsurface chemical explosions in Nevada, United States. And today, I'm going to talk about thermal photogrammetry, how we took from that into this new space. So first things first, kind of a general caveat, thermal sensors have lower resolution than traditional RGB cameras. What I mean by that is they have less pixels within their screen view than a traditional RGB camera would have. Thermal sensors, and this is thermal infrared, collect brightness temperature, which is best thought of as reflectance or intensity or basically those values for every pixel. And typically, when people are talking about a thermal camera, they're taking that value that the pixel has and converting that into a temperature. However, without a known value, such as a bucket of ice water or something like that, your calibration will be wrong. For the work we're talking about today, we don't actually care about the temperature of any of these objects we're looking at. What we care about is the fact that the reflectance of a metal fragment or an object following an explosion is very different than the surrounding landscape. So in our case, we can actually simplify our data by converting the thermal imagery just into a simplified grayscale and then using that within our photogrammetric workflow in order to be able to look at the site and see these contrasts between objects we care about and just the general landscape. So we got to do a specific study, and these are the questions that we tried to address within that. The first was, following a surficial explosion, so not underground this time, could we identify metal fragments and debris from the actual explosion greater than 10 centimeters? Now, the platform we use for this work is actually an UAS, and excuse me. In this case, this was based on the AGL, above ground level flight parameters we put into the system and the amount of time we had to do this experiment. The other questions we had were, could we process this data on a single machine? So can we do our photogrammetrics work without using a network of computers, but just on a single tower or laptop, such as being able to process it in a field or at a remote location? One other question we worked towards was, could we collect and process this thermal data without GPS tags on each thermal image, which is something done in precision agriculture and other techniques using similar thermal photogrammetric techniques. And then the last question we had was, coupling this data with thermal, RGB, and other sensors, can we identify objects in site disturbance beyond just the metal fragments following this explosion? We were lucky to be part of an experiment in Nevada, United States, involving a superficial chemical explosion that created metal fragments. We collected the imagery over 3 days, and our temperatures throughout those days ranged from 30 degrees Celsius to 46 degrees Celsius. Again, temperature does not matter in this case, just the variability between the ground surface and these objects. We also got the unique opportunity to collect imagery prior to, as well as following the experiment, in order to be able to filter out pre-existing material. If you're looking at a site, it may not matter depending on what you're looking for. I mentioned earlier, our platform was a UAS, so we used a 8-rotor small UAS. We mounted a FLIR Duo Pro R thermal sensor, which has both a thermal as well as an RGB camera to tie locations. And we also flew additional flights with a Canon traditional RGB, much higher pixel resolution camera. So I'm going to really try to quickly go through this workflow. For those of you guys who've done photogrammetry, it's probably very similar to what you've seen. In this case, for our thermal, we removed the imagery from the camera, and we converted that imagery into the grayscale, as I mentioned earlier. We used Agisoft Metashape as our photogrammetric software, which these photos were loaded into, able to do it on a single tower again. And then we ran that initial alignment. This is where those pixels to pixels are located, where the cameras are located, and a really rough 3D model of the surface is developed. Following that, we removed the poor quality photos, such as takeoff, landing, other ones that were just very blurry from the drone shifting and whatnot. We then began to tie it into our ground control points. Now, in this case, we did RTK surveyed ground control points, although you can use variable units for this. And once those were generated, we imported those into our Agisoft program, and then aligned these photos that had those ground control points in them to the photos that were there. This is an iterative process. You start aligning photos, and then you optimize the initial alignment again, and then you start aligning photos, and you do that until your accuracy and your values that you're looking at seem like they're more or less in the right place. After that, you generate a dense cloud, which is just taking that same pixel-to-pixel location and really, really emphasizing it and doing a lot more detail. You get a lot more points, and your locations are more or less set. You then clean that dense cloud, and from there, you're able to generate a surface digital elevation model, as well as the ortho image of the landscape you're looking at. I will note, in this case, it took 110 hours to complete this work. This processing time is super variable depending on the computer you're using, the experience of the analyst working on the actual manual steps, as well as a variety of other factors such as the number of photos, number of ground control points, and other stuff like that. So, first things first to highlight, this work actually worked. We were able to generate this thermal photogrammetric ortho image of the surface at our site. For those of you guys who are into pixel resolution, end of the day, our thermal resolution for each pixel was 10.2 centimeters. Our RGB imagery ended up being about 0.6 centimeters. And the digital elevation model, and I'll note this is resolution, not accuracy, was with about 1.2 centimeters per pixel size. From this, subtracting what we were able to see in the pre-existing imagery and thermal, as well as the DEM, from the newer post-experiment stuff, we were able to detect 105 new fragments, metal fragments, ranging from almost a meter to about 5 centimeters. Just to further highlight, the RGB imagery really shows the newly generated metal fragments, as well as some of the other site debris, as you can kind of see in that piece of wood there as well. The thermal imagery really shows those distinct metal objects compared to the surrounding landscape, which we were searching for. And finally, just to emphasize some basic geospatial tools such as edge detection, slope, and other built-in systems like that really help us look at that thermal and even quicker identify objects of interest. I mentioned earlier we were looking for objects that were 10 centimeters across, and you also may have noticed that I said 5 centimeters were some of the sizes we found. This is because by coupling thermal as well as RGB imagery, we were actually able to find fragments in the RGB that were smaller than our initial expected fragment size. Now, I'm going to close talking about some machine learning that we've started to do in this same world, and very preliminary at this point. This is within the ArcGIS Pro system. However, we'll talk about SVM and other stuff in a minute, but you could do this outside of it. Essentially, the workflow is creating a training and validation data set. As many of you guys in the MLAI world know, we want a lot of data. Unfortunately, that requires us to do some manual identification of fragments. So there's a trade-off of the size of the site you're looking at, the number of fragments you have available to you, as well as how useful that machine learning will eventually be. Once you develop and you decide on the size of your training validation data set, you can generate an unsupervised classified image where you're grouping the pixels within the entire image space together. You then run your supervised classification where you're actually deciding what those pixels mean. And in our case, we then take those classified thermal fragment fragments, and isolate those from the rest of the classification. And then we can hand those off to a geospatial analyst to start looking through all the identified potential metal fragments and really seeing if those are true or false positives. And I guess I'll highlight too, in this case, this was not subtracting out the post-explosion and the pre-existing materials. We detected 461 potential fragments using this tool set. This is actually what it looks like at the end of the day. I mentioned before, so within ArcGIS, we have random trees, which is a stand-in for random forest, as well as support vector machine or SVM. They both seem to work about the same in our experience. There needs to be more testing to see which is the preferred. I also would like to highlight that, again, creating that training data requires an initial time investment. So once you have your completed products, you actually need to take some time to train it in order to actually get this output. I think depending on the size of the area you're looking at, it will really affect whether or not this is a good choice or not. So to conclude, talk about some of our challenges for this work, as well as some of the next steps that could really advance this work. First things first, it should be highlighted, this workflow was able to generate these images. We were able to get thermal ortho imagery of our site using a slightly modified typical photogrammetric workflow. Using both thermal and RGB imagery, we were able to detect post-explosion fragmentation as well as other surface disturbances at the site. To also highlight, it seemed this work works with a thermal sensor, not the UAS. So you could mount this on the bottom of another airborne vehicle, potentially on a long enough stick, depending on what you have access to. As I mentioned before, the timeline to completion in this case was 110 hours. Regardless of what you're looking at, that needs refinement, and hopefully we can begin to reduce that as we understand what we're doing more. A general point is advances in sensors will allow for faster and higher resolution collections, both of the size of the pixels you're able to see from different altitudes, as well as how rapidly you can collect data and other variables. And finally, just to highlight, the MLAI methods could greatly reduce the time from collection to actionable data, depending on the size of the site you're looking at, as well as what you're looking for. And with that, I think I am done.
So we have time for one quick question. Laurel?
I badly want to sneak in too. One of them's super quick. It's just how many cores? When you say one machine, how many cores is that?
So I'm not sure in this case, actually.
Okay, let's go on to the other one. The other one's more important. It's can you just take a second and describe the scenario in which you think it would make sense to sort of not be entering an area on foot, but flying with the drone instead overhead to find out where the metal fragments are?
I think it really depends on the case. I don't have an exact example in this case, but it's more that we generate this tool set so that it is available in case there is a situation that could use it.
I think we are short of time, Brandon. I have a load of questions here. I'll see you later on about those. Maybe we'll come back to them at the end of the session anyway, okay? Thank you, sir. And we can move on to the next presentation by Anjan Chamuah, and he'll be delivering a presentation on unmanned aerial vehicle technology for nuclear disarmament, a responsible innovation perspective.
Thank you.
Anjan, you have the floor. Thank you.
Yeah. A very good afternoon to all. So I'm a person from social science background. I'm not going to talk about the technicalities behind unmanned aerial vehicle or for that matter any other technology. So I am going to look at technology from a policy and from a social science perspective. So my topic of research here is unmanned aerial vehicle technology for nuclear disarmament, a responsible innovation perspective. So bring from social science, how I am looking at technology, that's very important for me. What we understand from different literatures available on technology, is technology is not only a machine, it's a methodology. According to Biker, all technologies are socially constructed, and technology do have socio-political, cultural, and legal implications. So while deploying technology like UFV for a particular purpose or a particular objective, we must be very clear on the foresight of the technology, that what can be the impact of the technology for any purpose in coming days, say for the society, for environment, or for our culture. So, having said that, so your main aim is on nuclear disarmament, and we are trying to deploy technology called drone. So how can we fulfill the objectives? So these are some of my research questions. How for technology like UFV can fulfill the objectives of CTBT? How can the framework of RI, or responsible innovation, you might have heard about that theoretical framework, help in studying the issue of nuclear testing? So these are some of my research questions that I have formulated based on secondary literatures, based on some primary work that I have done on UFV, particularly in my country. I'm from India. So how such technology can be deployed responsibly? What are the issues hovering around the technology so that it can be beneficial for the society, it can have some values for the society, for the economy? So we all know what is UFV. It is an unmanned aerial vehicle which is controlled from a remote location by a pilot, and which again, see, these are some of the features that I want to show you. And different features attached with the technology. The single board computer is there. There are sensors, the global positioning system, etc., etc. So these are the main issues that I want to discuss here. See, when we talk about UFV, it's a risk mitigating tool. It's using intelligence, surveillance, and reconnaissance for exploration. And what I have seen that it's nowadays using other military purpose for crop cutting experiments, for spraying of fertilizers, etc. But when we are deploying such technologies to our society, there are different rules and regulations that govern the technology. So who are the actors and stakeholders? Are the actors, stakeholders deploying the technologies accountable for deployment? Are they responsible for any failure in coming days? So these are some pertinent issues that I want to raise when we deploy such technology to our society. And this is an emerging technology for us. Why I'm saying it's an emerging technology? Because the technology is in R&D stage, not yet implemented in entire society or the economy where I belong to. So having said that, now I'm moving to the theoretical framework that I have used for my study. It's called responsible innovation or responsible research and innovation. Why this theoretical framework is important for my research? Because I am deploying a new and emerging technology to our society. I'm responsible for any failure or harm that it caused to the society. So what does responsible innovation says? According to Stigley et al., they say that responsible innovation means taking care of the future. How we are taking care of the future? Through collective stewardship of science and innovation at the present. According to von Somburg from European Union, he says that responsible innovation means it's an interactive process where societal actors and innovators become mutually responsive to each other. They focus on societal acceptability, ethical acceptability, and sustainability. Von Somburg further says that when we are deploying, or we are responsibly deploying, or we are doing responsible innovation, we should contribute some values to the society, for the economy. Then only that innovation can be called responsible. Otherwise, it can lead to irresponsible innovation. And further, von Somburg says that irresponsible innovation is not an act of a single actors or stakeholders. See, in an innovation process, academia, civil society, industry, and the government forms a quadruple helix of model of innovation. So contribution of all the four stakeholders is very important in order to make the innovation responsible. So further, responsible innovation also takes care of other issues, like it takes care of economy and environment by engaging in 5 dimensions. What are the 5 dimensions? These dimensions are anticipation, that linked to foresightedness, reflexivity, cause and effect relationships should be seen, and the deliberation process is very much important, and participation of all the stakeholders. The responsiveness, how they're responding to the technology, is very important. So, why responsible innovation again? See, there are other innovation frameworks like technological innovation system, sectoral system of innovation, regional innovation system, open innovation. But why I have chosen this innovation approach? I do have reason for that. See, responsible innovation gives us the entire process from ideation to commercialization of the product, where we deploy such technology. It's an iterative process where we can trace from the beginning to the launch to the market. And if we combine these two structures, if we go by the initial definition of innovation by Schumpeter, he says that innovation is creative destruction. When we're destroying something, it should be replaced by something else, something productive. But again, sustainable development is also related with this theoretical framework. And we know what is sustainable development and what are sustainable development goals. We are caring for the resources, for the humanity, for the environment, for the people. And inclusive of all these things, innovation and sustainable development gives us the responsible innovation framework. It talks about governance issues. It talks about gender equality. It talks about ethics. It talks about science education, participation of all the stakeholders, and so on and so forth. That's why this theory of responsible innovation is very much important when we deploy such technology to the society, because we are answerable for any wrongdoing. And according to Colin Reed's dilemma of control, what Colin Reed says that technology should be controlled in the beginning of deployment, because at the later phase, the technology might permeate to other areas in the society or the economy. Then it's very difficult to control. So, having said that, embedding values in the design of the technology is very much important, according to Hoven. And how to embed values, and what are the values, that's very essential. Values like accountability. We must be responsible for what we are delivering through the technology. And it should give us accurate results. The technology must be efficient in their task. It should be concerned about safety rules. It should not hamper the privacy issues that are hovering in our society. It should have ethical clearance. It should have ethical acceptability in a society. So, these issues of UFV and responsible innovation is very much important from a perspective of emerging technology like drone and a very critical issue like nuclear disarmament. I'm not a technical background person, but I look at it from a social science. And these issues are very much important for us. When we talk about policy, while we talk about policy, the other actors, women participation, science education, these are very much important. So having said that, I conclude my talk, and the House is open for discussion and your comments and reviews. Thank you.
Thank you, Anjan.
Yep.
I will open the floor for questions and comments right now. I'd draw your attention as well to the poster session accompanying this oral session, which covers similar topics as well. There are various posters that cover this topic and other topics related to on-site inspections. So I would encourage you to look at those posters when they're available on Thursday, I believe at 10 o'clock in the morning for the lightning talks and the poster session afterwards. Any questions to Anjan? Nothing from the floor at the moment. I'm sure there'll be opportunities outside the session to talk to Anjan separately. So, Anjan, thank you very much. Thank you. So that concludes the 4 presentations we have. Gregor, if you can wrap up.
Yeah, thank you very much. Thanks a lot to the speakers, of course, and of course to the audience as well. As Arla just mentioned, there is this lightning talk session and subsequent poster presentations on Thursday morning, 10 o'clock, up in the Wintergarten. And there you'll see many more perspectives to OSI techniques. We've seen already a good variety today. And I hope that we continue our discussions off or outside these formal sessions also. We are approachable, and we'll hope to see you over the next few days. So thank you very much, and have a good afternoon.
Thank you.